all the fun of circuits. So Kirchhoff's laws, there's really two things that he mentioned, and they're both related towards the conservation of either energy, which is going to be related to basically voltages, and then conservation of charges, okay, which is going to be related towards current. So if you think back on the conservation of energy and you go into electrical circuits or in electricity in general, you may recall that voltage is nothing else but simply the change of energy with respect to the amount of charge, right? So that's how voltage is defined. Now I can put up a link up above there to voltage for you. I have no interest in redefining it here. I just want you to be able to understand why, okay, it is in terms of Kirchhoff's laws that it relates back to voltages and it brings them back to the conservation of energy. So the reason for the conservation of energy is because voltage is defined in terms of a differential potential energy that you have within electric circuits. Okay, so that is where the conservation of energy will come from. Now, what did Kirchhoff say about voltages and then voltage drops? So what is this first kind of law? Now, so this law is typically referred to as Kirchhoff's voltage law, and very often you're going to see it, okay, written out as an acronym KVL. So what he was saying is the following, that if you take any closed loop within a particular circuit, so I'm just going to relate it back to circuits, okay, within here. So if you take a loop, now what does it mean to have a loop, right? And this is kind of a closed loop. So now within here, you'll see that I have a battery within right there. I have some kind of a resistor, so this is a symbol for a resistor. I have another resistor over here. I have no idea what this might be, okay, so this might be some kind of a load. But what I want to kind of point out in here is we have a loop, right? So we have a particular loop. If you go all the way around here, it will create a closed loop all the way around. And what Kirchhoff said is that if you take this particular loop, now it doesn't matter in which direction. So, you know, I made it kind of clockwise. If you make it clockwise or counterclockwise, it does not matter. And you start thinking about the voltages. So I'm going to just call this. Let's say this is voltage number 1. This is going to be voltage number 2. This is going to be voltage number 3. This is going to be voltage number 4. Now, it doesn't matter how many voltage, okay, drops that you have. So it can be 3, it can be 2, it can be 5, it can be 100. So it does not matter as long as you have a closed loop all the way around. Now, you do have to define the voltages, so you kind of have to make a convention, okay, as you're going through. So what is going to be positive, what's going to be negative. So for instance, you know, I like to kind of write these out, okay, within here. So I'll make that positive, I'll make that negative. If you know what the voltage is, then obviously you don't have to be guessing, but I'm going to just make all of these in this particular direction. So let's say that those are all positives, okay, and then negatives. And then when you're creating your loop in here, so if I'm going to go all the way around and I create my loop, right? So this is my loop, okay, or a path all the way around here. Then this is what it says. So it just simply states that if you go around the loop, so I'm going to start now. It doesn't matter where you start, okay? You can start from here, you can start from here, or from here very often. So this is called the source, okay, on the battery side, where it's actually providing, okay, a voltage difference. Okay, so it doesn't matter where you begin. So I'm going to, let's say, start over here because I like to start from, as I draw my loop, on the positive ones. So this would have been simply V2, and then, so now why is it V2? So I'm entering, so notice my loop is coming in on the positive side. So my loop here is coming in on the positive side, so this is going to be plus V3. It's coming in here on the positive side, which is going to be V4, okay? But notice that this loop is now coming in on the negative side, so this is going to be minus V1 over here. And what Kirchhoff's voltage laws state is that around any loop that you take, all the difference, okay, will be equal to 0. So the voltage drops altogether are going to be equal to 0. Now, this shouldn't surprise you if you think about voltages and relate it back to the energy that the charges would carry. So the amount of energy, which is the conservation of energy, well, we can't really create more, okay? So it can't be a positive or a negative amount, okay, if you have a closed-in system. So conservation of energy within a closed-in system, the amount of energy, can't be created, can't be destroyed, it can only be transferred. So this is based on that principle. And if you take any loop in here, okay, so this is what you're going to get. Now, very often, because of the fact that you have this battery, which is kind of the source within here, you might actually bring this over, okay, on the other side. So sometimes it might be written like this, where, the V1, okay, right here, because it's on the negative, is going to be equal to V2 plus V3 plus V4. So you can certainly write it out like this, okay, if you wanted to. But the idea is that the sum of all of the voltage drops, okay, around a particular loop is going to be always equal to 0. So this symbol just means the addition, so the sum of all of the different voltages around a particular loop is equal to 0. So that's Kirchhoff's voltage law. So there you have it in terms of a particular circuit example right there. And it does not matter, again, in which loop you go. So you can do counterclockwise, okay, or clockwise, okay, so one or the other, it does not matter, all right? Now, the other Kirchhoff's laws, okay, that he has noticed is related to the conservation of charge. So that means we can't really create, okay, or destroy charge. I mean, charges can come together, certainly, but that doesn't mean that they have been created or destroyed, right? They might just balance off each other. So positive and a negative, okay, could balance off to a 0. But still, the overall charge is going to be the same. And that's the conservation of charge. And what that relates it back into is currents. So now, if you think back of currents, I'm going to switch the color in here. So current, instead of a voltage, so we had a current was equal to how much charge is actually passing by a certain amount of time, right? So this is related back to the amount of charge that you have, hence the conservation of charge. And what it says is that you cannot create or destroy charge. It has to be summing up in total to the same thing, okay, overall. So here is another example right here, which I want to be able to illustrate now, Kirchhoff's current law. And Kirchhoff's current law, so that one is typically KCL. So, the voltage one, as I mentioned, is typically known as KVL, so Kirchhoff's voltage law. So that's the summation around the loop of voltages is equal to 0. And for Kirchhoff's current law, what it states is, if you take a node or some kind of a junction, now you have to kind of think back of, okay, what does it mean to have a node or a junction, okay? But, okay, so instead of me jumping right into this example, okay, so I'm going to kind of make it a little bit simpler for us. So if you have some kind, okay, of, let's say this is called a node or a junction, and, you have wires, okay, so that are coming into this junction, and then maybe they're coming out of this junction, okay? So, coming in and coming out does not matter, okay, what we call coming in or coming out. So in total, because of the conservation of charge, again, this should make sense to you, is that let's say that you have a current coming in. So let's call this current number 1. It's coming into this junction, right? Let's say you have another current and this one is coming into this junction as well. So this is current 2. Let's say over here, this one is coming out of the junction. Let's call this current 3. Okay, this one maybe is coming into the junction, which is current 4. And then maybe this one is a current, okay, which is coming out of the junction right there, or this node. So what it says is, because the conservation of charge, okay, so just like your conservation of energy, well, the total charges coming in and coming out must be the same. So they must be equal to the same amount. So there's two ways of thinking about this Kirchhoff's current law in here. So what it can say is the following. So it means that all your currents coming into a node are going to be equal to 0. So that's one way of thinking about it. So coming in is positive. So we can say that the coming in is positive. So what's coming in? I1 is coming in. Notice I2 is coming in. So this is going to be plus I2. I3 is coming out. So that means I'm going to put minus because it's coming out of the junction or the node. So that's I3. I4 is coming in. So that's going to be plus. Okay, so I4. And then I5, I guess this is I5 right here. I wrote I4. So this is coming out, so this is going to be I5. So coming in positive, all right, coming out negative. And all of this is supposed to be equal to 0, which means the total charge coming in and coming out have to be equal. So very often, you know, you might write it like this, or you might just simply write it like this. Okay, whatever is coming in, so I1 plus I2 plus I4, which is coming in, is equal to whatever is leaving, which would be I3 plus I5. Now, of course, these two equations are identical because all you're really doing is you're moving these two terms on the other side. So that is Kirchhoff's laws. Those are the two laws that we have. And now they're extremely powerful in a sense, because when you're talking about circuits, you have to kind of get used to the fact of thinking about what these nodes or junctions or these loops or paths are all about. But once you do, you know, you can create really nice equations for these. So for instance, if this is, you know, our actual circuit that we have, I'm going to try to illustrate both Kirchhoff's voltage law and then Kirchhoff's current law. So let's stick to voltage laws, you know, so I'm going to label all of these out. So let's call this, you know, V, okay, this is, you know, number 1, okay, and then this is the drop from positive to negative. So again, you would have to kind of label these out. So positive or negative, you can say this is positive or negative, okay, this is positive or negative. And so what we have is we have some kind of a source right here, so some battery, we have another battery over here, we have two resistors, okay, over here, and then we have something which we don't really know, all right? Now, once you label these out, so let's call this V2, you know, let's call this V3, let's call this V4, and let's call this V5, all right? So this is what we have. So now you can create various paths along this, right? So kind of closed loops as you're going through. So I'm going to create, you know, all of them just so that you can understand, okay, how you can apply Kirchhoff's voltage laws. Okay, so we have, so how many loops can I create here? Well, so there's one loop which I can create, and this is going to be a closed loop over here. So this is going to be my loop number 1. And now within this loop, what it would mean, so as you can see there, so this is going to be V2, okay, so plus V3, okay, and minus V1 is equal to 0. So that's from Kirchhoff's voltage law. So we have a very closed loop, okay, so notice that this is my loop, okay, and it circles all the way around and comes back and it's closed in. So that's what I have there. Now I have other loops as well in here. So notice that I have another loop that I can create over here. So I can create loop number 2, okay, over here. And this is from loop number 2. So what we have is, so this is, I'm going to just go, so V4. Again, it does not matter which one you start with. So plus, let's say V5, and then minus V3 is equal to 0. All right, so that's another loop, and this is coming from Kirchhoff's voltage law. So I have two different loops. Now, are there any other loops? You might think, well, it doesn't seem like it, right? Well, there is. There is one particular loop in here. Now, this one is a little bit harder to notice, okay? But as you're going through, so notice that you do actually have a loop, okay, all the way around, okay, if you can create a loop in this direction, right? So that could be your next kind of loop that you have in here. So if I'm going to kind of shift this a little bit over for you. So here's my, you know, my last loop all the way around, okay? So going back, okay, through this, let's call this loop number 3. So now this one, how it would look like would be V2, okay, so plus V4. Now notice I'm not going through here, right? So I can't be counting this one in here. So because I'm going all the way across that way. So that's V4 plus my V5 and then minus my V1. And that is equal to 0. So that would have been 3 different loops that I would have. Now, the other component is, so if this is my KVL, there's really no other paths I can make. I mean, I can surely go in a counterclockwise, but it would produce exactly the same equations for me. So the voltage drops in general. So that's what I would have. So the next thing that I can do, so, forget these loops. Let me kind of remove them within here. And now I can talk about currents, all right? So for currents, what we would have is, so we have currents coming in are equal to the currents coming out. So now again, so you can certainly label all of these. So you can, for instance, say, okay, so that is, let's say my current number 1, okay, so it's going to be current going in this direction. Now you might say, how do you know which direction it flows? You don't. You just make a convention and you make an assumption. And if it turns out, because later on when you do examples, okay, if it turns out that your value is negative, that means that you just made the wrong assumption. So it's actually in the opposite direction, right? And that's not a problem. So the first step to do is you actually assign currents, okay? And you provide the direction in the actual circuit. So let's say I have a current which is coming out from that source right there, and it's going in. Now, the question now becomes, what are these kind of nodes within here, right? Or these junctions that I have? Like, where can I find them, okay, in here? Well, so, very often when I started this, I would think that, oh, this is an actual node. Well, no, not really, okay? So because this entire thing right here, okay, is basically connected together. There are no resistors, no actual loads. There's nothing in here. So this entire thing, sure, it's it can be considered a node, but if you look at the current, so this current coming in, if you label this a node, you would have a current which is coming out, okay? And these coming in and coming out, they have to be equal, right? The junctions and the nodes happen when there is a split. So when there is a split, when there's actually more kind of than just one path coming out. So I wouldn't need to label any current in here because it's still the same current. It's still I1, which is just flowing all the way through. But here, now I do have a split because I have a split going in this way and I have a split going in this way. And this would be considered a node or a junction. So right there, we do indeed have to think about, all right, what are our currents? So we have now labeled our current 1, which is coming into the node. And now I can have 2 separate currents. Okay, let's imagine that this is going to be my current number 2, which is flowing out. Okay, and for the sake of this example, assume that this is my current number 3, which is going to be flowing in this way. And notice, once you make that assumption, so that current is going to be flowing all the way into here, right? This current is going to be flowing through here, and it actually flows through here. Now, notice this is a positive and a negative. So because of the positive, we might think, maybe it's actually going in this direction. We wouldn't know that until we could analyze the circuit, okay, and actually solve this. But we have no values in here, and I don't present you any values. I just want you to understand how do you set up these current laws with respect to Kirchhoff's. Okay, so this current would have been flowing into here. It's going to be flowing, we'll assume that it's flowing in this direction, and then it would come back, right? So this current over here would join back with this one, and it would flow back into here, and notice that it forms I1, which is exactly the same thing, right? I1 is going in, okay, and then I2 is coming out, and then I3 is coming out. So within here, if you were doing Kirchhoff's current laws, so really there's kind of just one junction in here where you have I1, which is going into the current, minus, okay, I2, which is coming out into the node, my apologies, and then I3, at least my assumption, okay, would be this. So that would have been another kind of equation that I could add in, right, as you're going through. So this is another nice example where you can take a look at these Kirchhoff's voltage laws and Kirchhoff's current laws and how they work. Now, if you wanted to create another one, if you wanted to call this another node, so this is coming in, we don't typically do that in here because it's going to be a overkill, because it's going to yield exactly the same equation, except the signs will change because I2 is coming in, I3 is coming in, and I1 is coming out. But of course, if you rearrange this, you can bring these two terms over on the other side, and all it says is that I1 is equal to I2 plus I3. That is the conservation of charge, okay, within the flow of this particular circuit. So when you're beginning these are not going to be super complicated. They're going to be like this, okay, so very much so, right, as you're going through. So the one thing that you should note, which is actually very common, okay, and it stems out from the KVL and KCL, so I'll just refer to those voltage and current laws, okay, in the acronyms moving forward, is this idea and concept behind things that are in series and things that are in parallel. And that's something that you should be aware of, all right? So here is an example, okay? So this is what I mean when things are in series and things are in parallel, okay, when you join them together. So here's another circuit. Now this circuit, there's no resistors. This is actually, a symbol that I want to present to you. So this is kind of like a light bulb, okay, that you would have. So you have a bunch of light bulbs, okay, within here. You have your battery symbol right there. You have a switch symbol right here. So notice the switch is open, so current can't really flow, right? Because it's not a closed path that we have. We have no closed paths in here at all. So as you're going through, so in order to make this, okay, and make the current flow throughout, you would have to take this and then you would have to close it, right? So you very often will see these switches as you're going through, also as signs as you're analyzing. So don't be surprised, it just means a switch where you can just open things up and close circuits as you go. So what I was referring to in terms of parallel and in series. So what you have in here is you have a battery. So notice that it's going to be attached to this light bulb, okay, and this light bulb. These two light bulbs are connected in series. Okay, which means that if you would cut this off, then there's no way that the current could flow, right? Because the current is going to be flowing, here, and it's going to continue flowing as you're going through in here, right? So within this path, these two are in series, and it's in series with this one, where it doesn't matter if you would close any of these or open, okay, any of these, current can't flow. Now, in parallel, what we have is when two things are in parallel, or maybe when three things are in parallel. So notice that it literally means, so if you think back of parallel lines, so if you create these parallel lines, okay, you could say that these two things are in parallel. And notice that if you cut one of them off, so if I would put a switch here and I would open the switch, the current can still flow, and it can still flow in this way, and then it would be able to flow in this way. If you would cut this one off, okay, well, then the current can still flow and it would be able to follow in this way. Now, if they're both attached, of course, the current is going to try to flow in both directions. Now, if they're the same light bulbs, it's kind of evenly going to spread out. Okay, so that current. So if you're thinking about what does it mean to be in series and what does it mean to be in parallel, well, this is exactly it. So you can have, so for example, if you take resistors, right? So you can take resistors, you can connect these resistors in series. So these are all in series as you're going through, okay? And you can create resistors which are, for example, in parallel or anything in parallel, okay? And typically, this might look something like this, okay? Where it's flowing through, maybe you have another one, maybe you have another one, okay? And so on, maybe you can connect as many as you like. But these are all in parallel. And the main thing with regards to this, when you're relating it back to Kirchhoff's laws, okay, so if you have something in series, notice that the current would just flow. It's going to be the same exact current through all of these when they're in series. But here, the current is not necessarily the same because the current can be coming in, but then it can split. So you can have multiple currents in here. So when it's parallel, so because it's going to be splitting amongst all of these, depending how many you have. And that comes from KCL, right? So the current coming in is equal to all the currents coming out, right, within here. Now, in terms of the voltages that you have, well, there will be some voltage drop across all of these. But notice that if you have something in parallel, so I'm going to kind of go back in here, you can create a loop here, right? So you have a closed loop all the way around in here. And so if you would label this out, so let's make this positive and negative, positive and negative. So if I would call this, let's say V1, okay, and then call this V2, and I would create a loop in here all the way around and apply Kirchhoff's voltage laws, then what you notice is you have that V2, right, minus V1 is equal to 0, which implies that V2 is equal to V1. So in parallel, so it doesn't matter how many things you have connected from Kirchhoff's voltage laws, we notice that the voltage across here is going to be identical to the voltage across here. And indeed, this entire thing is just one node, and so is this, right? So that's just one junction, okay, that we have. And it's going to have the same identical voltage drop. These lamps, okay, or these bulbs could be actually different, okay, or they could be resistors, which are of different size. One can be 1,000, one can be 1, and yet they still will have the same voltage drop if they're connected in parallel. All right, so that's the introduction that I wanted to give you with respect to KVL and KCL. You should see, quite a few examples, okay, and numerical examples, which I'm going to present, okay, so you'll find that, so that once you watch it, okay, it's going to start making more sense, and you're going to know how to apply these things throughout. All right, thanks for watching. We'll see you in a future video. Bye, everybody.